This video is on transform feedback. If you've tried following a tutorial on particle systems or physics simulations in WebGL, you probably had to use one of these. Now, I don't know if you're like me, but my first few times trying this were pretty rough. Particle systems themselves aren't insanely complicated, but they're not exactly trivial either. And the same goes for transform feedback. Not insanely complicated, but not trivial. But having to learn both at the same time and having to get both correct before my program worked, that was kind of gross. What I built looked to me like spaghetti code. It was incredibly brittle when it worked at all, and debugging it was baffling. But then once it's working, it's time to move on, and that's the last you hear about transform feedback. And that's too bad because, weirdly, transform feedback syntax and usage actually isn't that complicated at all. And it's an incredibly powerful tool that has a lot of uses beyond particle systems and physics sims. It's just that there aren't many places that explain them in isolation so that you can learn about just transform feedback. So that's what this video is about. We'll talk about what transform feedback does and how it's typically used. We'll do an overview of the syntax. And last, we'll slowly build out a simple application, starting out as bare bones as possible and keep adding to it until it's something more usable and realistic. When you add transform feedback to your WebGL2 program, you're telling WebGL to record certain outputs from your vertex shader. That's it. It records only the outputs that you specify in the order that you specified them. It does that for every vertex in your draw call, and it saves those outputs to an ordinary buffer, one that you provide. After you tell WebGL to start transform feedback, then every time your vertex shader is executed, so that's once per vertex in every draw call, that output will be saved to that buffer. And that's all it does. It writes vertex shader outputs into a buffer. And once you tell WebGL to end transform feedback, it'll stop storing outputs and you're free to use that output buffer however you want. So imagine you have a dozen objects. Doesn't really matter what they are. Could be just raw geometry, or they could be individual instances of some less abstract thing, like fireballs or glowing embers or raindrops or bullets or blades of grass. Doesn't matter. All objects will be the same kind of thing and share the exact same attributes, but each will have its own state, which is described by the values of those attributes. And maybe every animation frame, you'll want to update these objects, apply the same logic to each one to convert its previous state into its next state, to move it or rotate it or rev it up or cool it off or whatever that object naturally does over time. This kind of state manipulation, we do this in JavaScript all the time, but hundreds of thousands or even millions of objects, 60 times a second, maybe not such a great idea anymore, especially when your CPU needs to be doing a ton of other things at the same time, like managing a game. Well, you could use multiple CPU threads to distribute the load. Modern browsers have web workers, right? Well, yeah, but instead of adding a few extra CPU cores, how about doing it all with hundreds or even thousands of GPU cores? Move all that state data into the GPU's memory and add those state calculations into your vertex shader. You get to use all that massive parallel execution power, and your CPU's left to do other things, or just twiddle its thumbs. So that's what this is all about. Moving your state information onto the GPU, moving all of your update operations onto the GPU, and leaving the results of those updates on the GPU where it's immediately ready to be used again. This way, not only will your updates finish a lot quicker, but now you don't have to upload that data anymore from JavaScript. This is a rough summary of what WebGL's transform feedback looks like in an application. It may seem like a lot, but really it isn't. In fact, this is the only new stuff that you need to learn. Everything else should be completely familiar. There are 3 stages to this. We start off with the vertex shader before linking the program. We specify the outputs in our shader source, and we tell WebGL that's what we want to save. Next, we prepare our buffers. This is where our transform feedback outputs will be written, and it's no different really from any other buffer code that we've ever written. And last, we make the draw call. Here, we tell WebGL to use the buffer that we created, begin recording, issue a draw call, and stop recording. And we're done. Now, let's review the syntax of these new transform feedback functions. We're going to start first with transform feedback varyings, since this is usually the first actual transform feedback function your program will call. This must be called before linking your program. You can call it afterwards, but it won't take effect until you relink your program. Transform feedback varyings is for telling WebGL which of your shader outputs you want to record. The first argument is the program. The second is an array of the names of the varyings that you want to capture. Of course, your vertex shader may have all sorts of output varyings. Some will only be for the fragment shader, some will be for transform feedback, and some might be for both. So this tells WebGL which varyings to record. Also, the order of this array determines the order the values will be written to your buffer. And the last argument is the usage type. There are only two possible values. There's separate attributes, which means that each output varying will be saved to its own buffer. So if you have two output varyings, you'll have to provide two buffers. And there's interleaved attributes, which means that the output varyings will be written one after the other into the same buffer. As always, there are hardware limits. If you use separate attributes, you're limited to 4 outputs. The spec says that the limit is hardware dependent and that you're always guaranteed at least 4, but 4 seems to be the only value that you'll ever encounter, even on modern hardware. And if you use interleaved attributes, you're guaranteed a minimum of 64 interleaved output varyings. Before we move on, I just want to warn you that the next 2 functions look essential, but are actually sometimes completely optional. In fact, we won't even be using them in our code example today. I'll explain why in a second. The first is create transform feedback, which creates an object for managing your transform feedback operations. And the second is bind transform feedback, which binds it. When you bind a transform feedback object, WebGL will use that object to keep track of whether transform feedback is active, which buffers are bound, and how far along it is into its buffers. If you have a program with multiple unrelated transform feedback processes, you definitely want to use these to keep them separate. You can also use transform feedback objects sort of the same way that you use vertex array objects. Remember how VAOs allow you to move certain vertex array functions out of your render loop and into your initialization code so that you can replace these functions here with a VAO that already contains them? Well, transform feedback objects can do the same thing. It means that you can move all of your BindBufferBase calls out of your render loop and replace them with bind transform feedback. However, WebGL 2 actually has a single default transform feedback object that's been available to you this entire time that you've been writing programs. That object can't be deleted. In fact, when you call bind transform feedback with null, you're just switching back to that default object. So often, you don't even need to call these functions. Okay, let's keep going. Before beginning transform feedback, we need to call BindBufferBase to identify the buffers that we'll be writing to. Now, we met this function a few videos ago when we looked at uniform buffer objects, but the arguments here are all a little bit different now. The first argument is the target, which now is transform feedback buffer. Next, the index value is a bit different too. Before we got to pick our own index however we wanted. This time, we can't. If you're using separate buffers for your outputs, then this number here will connect a buffer to the varying output at that index. For example, if you have 3 outputs, an index of 0 would connect the buffer to the first output, 1 to the next, and 2 to the last. But if you chose interleaved outputs, then this number is just 0. And finally, the third argument is obviously the buffer. Begin transform feedback is how you tell WebGL to start listening for output. You have to specify the primitive type here, and you're restricted to only points, lines, or triangles. And in WebGL 2, you have to use this same primitive type in your draw call, which means you can't use triangle strips while doing transform feedback. In OpenGL you can, but in WebGL you can't. There's another important restriction. You can only use draw arrays and draw arrays instanced. If you try to use draw elements or draw elements instanced, WebGL will throw. Now, these restrictions only apply to when transform feedback is active. Once you've ended transform feedback, you're free to use that buffer data however you want, which includes using triangle strip and draw elements. You just can't do it while transform feedback is still going on. And to end transform feedback, you call end transform feedback. Do that and your output buffer is now ready for whatever it is that you want to do with it. That takes care of all of the main functions that you need to know about, but there's still 3 more that are worth mentioning. Delete transform feedback is for cleaning up after you've completely done with transform feedback. You'd only use this if you also used create transform feedback. Also, there's pause transform feedback and resume transform feedback. Pausing after completing a draw call is typically done so that you can load up different data or load up an entirely different program for another draw call. And this means that you can store outputs from multiple draw calls all to the same buffer. So that's the syntax, but before we get into some actual code, I want to take a couple of minutes to talk about binding points and buffers, because these are about to become a new and frequent source of errors. Here are the 2 new binding points. Note that transform feedback is only used with bind transform feedback. And since this function is often not needed, this target is also often not needed. Transform feedback buffer, on the other hand, works with a whole lot of other functions. But notice how similar this list is compared to array buffer. The only function that's unique to this target is BindBufferBase, which we will be using here. So does that mean that we don't need to use array buffer anymore? Not quite, because of this. It may not be immediately obvious why, but let's think about this. After transform feedback, we're probably going to want to use that output data for something, maybe to draw to the screen. So after using our buffer as a transform feedback buffer, we're going to need to treat it like a regular old vertex array buffer. The only difference is that now we don't have to upload data anymore, but everything else, it's still the same. We'll still need to call enable vertex attrib array. We may still have to call vertex attrib divisor if we use that. And we'll definitely have to call vertex attrib pointer, which means we have to bind to array buffer. However, this raises a serious but subtle problem, and for me, the most common source of errors. We use BindBufferBase to bind our buffer to transform feedback buffer, right? That tells WebGL to write to that buffer during the draw call. Then later we use BindBuffer to bind that same buffer to array buffer. That tells WebGL to read from that buffer during the draw call. That means it's possible, if you're not seriously careful, to bind the same buffer for reading and writing at the same time, which will throw an exception. Your program will crash, and it will be incredibly hard to figure out why. So, I have a few recommendations. First, I recommend that you become meticulous about cleaning up after yourself. When you've finished working on a buffer, unbind it. Like when you've finished creating and initializing your buffer, unbind from array buffer. And after each animation frame, after completing your transform feedback operations, unbind from both array buffer and transform feedback buffer. Second, when setting up your buffers, I recommend sticking to array buffer for those operations. You've been doing this since the beginning anyway, so this is just one less thing to change. Besides, if you end up using vertex array objects, you won't have a choice. And third, use vertex array objects. We already know how much it can simplify our render loop code in general, but when you're using transform feedback, it makes your code so much easier to decipher because the only binding point you'll see is transform feedback buffer. We'll see this in action in a couple of minutes. Now, buffer sizes are pretty intuitive, but they're worth exploring. Imagine we want to record all the outputs of this vertex shader. A vec4 is 4 floats, so 16 bytes. Add on another float, that makes a total of 20 bytes every time a vertex passes through the shader. So if this is our draw call, we'll be drawing 100 triangles, which means 300 vertices. 300 times 20 bytes per vertex, that means our buffer must be at least 6,000 bytes long. And if this is our draw call, then we'll be drawing 10 instances of 100 triangles. So 10 times 300 times 20, that's 60,000 bytes. If you do your math wrong and allocate too little space, WebGL will throw. But another common runtime bug happens when your draw call sizes are dynamic. Draw too many primitives or issue too many draw calls for your buffer size, and your program will throw. Okay, finally, time to write some code. We're going right back to the beginning again. This is our hello world example. It has a single draw call, which currently is drawing a single point primitive to the canvas, which means the vertex shader is running only once. So in effect, that's a single vertex. But we can make this even simpler. Let's clear out the fragment shader completely. You don't have to, but it's also not unusual to do this with transform feedback, to use transform feedback just to update a buffer that'll be used by a different program in a later draw call. But here, I'm just doing it so that there's less code for you to think about. So that causes an error. WebGL expects there to be a working fragment shader with actual color output, but we can fix that by telling WebGL to ignore the fragment shader completely. That means everything after transform feedback will be skipped during the draw call. Again, totally not unusual with transform feedback. Let's just remember to revert back when we're done. Next, let's add a couple of outputs to our vertex shader. We'll add 2 floats, output 1 and output 2. Inside the shader, these can be in any order that you want, and we'll assign values to each statically for now, so that we can see where our data is going when things are working. Notice that right now we have no inputs coming into our vertex shader, and that's okay. For now, let's just worry about output data. Next, let's tell WebGL to record these outputs using transform feedback varyings. And the order of these is important. Let's put output 1 first and output 2 second. Just for fun, let's try saving to separate buffers by specifying separate attribs. 2 buffer varyings means that we're going to need 2 buffers to record these outputs. Begin transform feedback, issue our draw call, and end it afterwards. And this causes an error because we've not bound any buffers yet. In fact, we've not even made any buffers yet, so let's do that now. Create a buffer, bind it to array buffer, and allocate enough memory for it using buffer data. How much to allocate? Well, let's plan for 1,000 point primitives. Okay, and 4 bytes per vertex. That's because each output is just a single float. And set the usage as dynamic read. I'll explain this a bit later. And do the same thing for the second buffer. And remember to unbind from array buffer. And before begin transform feedback, we have to call BindBufferBase. We have 2 buffers. Remember that output 1 is the first output, so its index is 0. Let's assign that to buffer 1. And output 2 is the second output, so its index is 1. Let's assign that to buffer 2. And after we're done, unbind. And when we run, no errors. We drew a single point primitive, so at this point, the first buffer should have a single 1 at the top of it, and the second buffer should have a single 2. Let's take a look inside these buffers and find out for sure. The code I'm about to write here isn't necessary for most programs, and it's not particularly fast, but here's how you can read the data from a buffer on the GPU using WebGL. Get buffer subdata. The target you use here doesn't really matter. Both transform feedback buffer and array buffer work fine. We could provide a data view here, but since we're just dealing with floats, we can use a float32 array. We'll be reading a single buffer right now, which contains 1,000 floats. Now we can bind to it and log the result. And buffer 2 does in fact contain a single 2. If we change our draw call and draw 1,000 points, we'll see that they're all 2s. And buffer 1 is all 1s. This next part really has nothing to do with transform feedback, and you absolutely can skip this part, but I just want to show you how to get rid of that warning. Plus, I think it teaches us something interesting about the WebGL pipeline and how asynchronous things are on the GPU in relation to our JavaScript code. So let's see how we can silence that warning. This code creates a sync object. You can think of it as a flag that WebGL drops onto its conveyor belt of tasks. And WebGL won't set that flag until it's finished everything else that came before it. In this case, the last thing that we did before we created this sync object was stop our transform feedback and do a little bit of cleanup. So this flag will tell us when our transform feedback buffer is ready for reading. There's no callback for this, so you'll need to check the status of this flag by polling WebGL with client wait sync. There are 4 possible statuses. If you get timeout expired, it means that the flag hasn't been set yet, so you should poll again. If the status is wait failed, then something bad happened. Usually you lost your WebGL rendering context. The only other possible values are condition satisfied or already signaled, both of which mean that the flag's been set and the buffer's ready for reading. And since we don't really care about which of these 2 statuses we get, we can actually just ignore this result and read from the buffer when we get there. And now the warning's gone, and we see that buffer 1 is full of 1s and buffer 2 is full of 2s. Now let's try this with interleaved attribs. Remove the second buffer since the outputs now will both go into the same one. We also need to double the size of the buffer to make room for both outputs. And now we're seeing the values of both output 1 and output 2 interleaved in the buffer. We're not looking at the whole buffer here, so let's fix that. And now we see its 1s and 2s all the way through to the end. Now, instead of a static value, let's try something more dynamic. Let's set output 2 to the vertex ID. That's an int, so we'll need to convert it. And now we can see that each vertex output has been saved in the right order right to the end. Okay, now let's deal with outputs and inputs. Add a couple of attributes and modify them so that we can tell them apart. Since we're not using any vertex buffers yet, then by default these attributes will come in as 0. And when we save, we see that happening. No surprises here. So now, let's use buffer 1 to hold our input data, our vertex buffer data. Add some initial values. We'll just use the index number of each value in the array. In our draw call, we'll need to tell WebGL how to unravel the buffer. Again, this is completely normal WebGL code that we've written over and over in this series. And when we save, 2 things. First, buffer 1 started out with our input data, so the numbers of 0 through 1999. So it makes sense that we see evidence of those values here. But our shader is also adding 0.1 or 0.2 to these values, which we're not seeing. And second, we're getting a warning that we've bound our buffer as both a vertex buffer, so as an input, and as a transform feedback buffer, so as an output. And that's forbidden, which is why the buffer's not getting updated. So we need to bind a different buffer to transform feedback buffer, and we happen to still have buffer 2's code available. Let's bind to that. Buffer 1 is twice the size now, so we should make buffer 2 that same size as well, and leave buffer 1 bound to array buffer for the inputs. Looking at buffer 1 now, we see that the correct inputs are still there, and when we look into buffer 2, we see that either 0.1 or 0.2 has been added to each initial value, which is exactly what we wanted. Now, how about making it so that buffer 1 and buffer 2 can be used interchangeably? Here, it really makes sense to add vertex array objects. So now our vertex attrib pointer calls are part of the initialization rather than the draw call. And in our draw call, we don't have to worry about explicitly binding the buffer to array buffer anymore, since VAOs do that for us automatically. Do the same for buffer 2. And now instead of this code, we can bind our first VAO, which does the same thing. And everything still works. Next, let's swap the buffers and try a second draw call. No errors. So now let's take a look at what's in buffer 1. And as you can see, rather than 0.1 and 0.2 on top of the initial values, we now have 0.2 and 0.4 added on. So these values have definitely been updated twice. Go a step further. We can repeat this 100 times. Create an active VAO and an active transform feedback buffer. Initially, these will point to VAO1 and buffer 2, and swap them every time that we've finished an iteration. And working fine. And this is the basis of most transform feedback operations that you'll ever do. You'll be doing transform feedback and then swapping buffers, and then doing transform feedback again and then swapping buffers over and over. Though instead of a loop, you'll be doing this with request animation frame. Okay, last point and then we're done, I promise. Remember when we allocated space for our buffers on the GPU? Back then we specified the usage as dynamic read. When we started, this was probably the right choice, but now it's arguably not. Let's talk about this for a second to figure out why. The value is a hint to WebGL how the memory will ultimately be used. In theory, the hardware may use this information to decide where to write the data in GPU memory. You can't be sure that the GPU will listen to your hint, and you can't be sure that the GPU won't change its mind after it's been running your application for a while. But it's a good idea to try and start out with the right hint anyways. These hints have two parts to them. The first half has to do with how often you intend to change and use GPU memory, and the second has to do with what you intend WebGL to do with that data. Static is for data that you don't intend to change, but that you'll read often. Consider this for data that you consider immutable, so not your first choice for a buffer that you'll use for transform feedback. Dynamic is for data that you intend to change often and read often. For transform feedback and double buffering, this is what you'll be using most of the time. And stream. This one is peculiar and somewhat rare. It's for data that you write once and read very few times. In general, this would be for when, instead of using buffer subdata to upload fresh data, you just call buffer data and create a completely new buffer every animation frame. This does have its use cases, but they're generally pretty advanced. So that's the first half of this usage value covered. The last half has to do with what we're going to be asking WebGL to do with our buffer memory. Draw is for data that you intend mostly for screen rendering. Read is for data that you intend to read back into your JavaScript like we did in our example today. And copy is sort of like both draw and read. It's for data that will be written to and read from just by WebGL. So JavaScript's completely out of the picture here. So if our buffer was used in a particle system where we weren't constantly setting new values from JavaScript and where we weren't reading values back into JavaScript, you'd probably want to change these hints to dynamic copy. So let's do that. And do a little cleanup. And we're done. So that was a long one. I don't expect this video to get a whole lot of views, but I know it will be helpful to some of you. At least, I hope it is. I really hope you have fun writing whatever it is that you're writing, and we'll see you again next time.